Okay, guys, good morning. How's everyone doing? Welcome back. And it's just a couple of seconds, I guess, 30 seconds or so, and then I'll get things started today. But I hope everyone's doing well, having a good week. And yeah, I'd be right with you. Hi, guys. Good to see all you. One second while I open my notes here. Okay. Okay, guys, welcome back. Hi, Kylie, Sebastian, Claire, Olga, Simon, Angel, Nigel, Zoe, Corey, Sydney, everybody that's here. Good to see you guys. So let's continue where we left off last time. We are now at the point in the semester where we're dealing with a current new topic, which is metaphysics of time. We're trying to understand the concept of the modern day theoretical understanding of time and how it is different from the classical Newtonian conception that existed before it. The first piece that I wanted us to look at was the work of Einstein, which we started covering in the Wednesday meeting. So the first step today, I just want to kind of review the major points from the Einstein lecture, and I want to add a couple of additional pieces of information to that so that you have an even more in-depth understanding of it. And then with whatever time we have after that, we'll start talking about Ted Sider's article, which is just called Time. Okay, so as we are now investigating the concept of time, we look to one of the great scientists and philosophers on that subject, which is Albert Einstein. And he says this in his paper that we looked at. He starts off with what appears to be an easy question, but it's not so easy. He says, okay, imagine that there is a railway embankment. Like, say, this is the, okay. Never mind. You know, I thought it would be better to have the panel that was further in front, but for some reason it's like haunted. So I'm just gonna let that go and work with this one. Thank you. Yeah. Okay, so my bad. Let me just tilt this a bit. Everyone can see better. Bring it up just a bit forward. Okay. Thanks, guys. So here we go. The railway embankment. Say this is a railway embankment where like trains travel. And here's point A and here's point B. Let us suppose that there are two lightning strikes which happen at these two respective points, A and B. Now, Einstein says, I want you to just assume that they happen simultaneously. Suppose they happen simultaneously, and then his next question is just this. What does that mean? Can you tell me what it means for two events to be simultaneous? And he says, it's actually not so easy as it seems at first to define, because any attempt to say what simultaneous means is going to run up against circularity. Try it yourself. Two things happening at once, two things happening at the same time, not happening at different times. What all these things are saying is just same time as, which is the same essential concept as simultaneous. But we're asking a deeper question. What does it mean for two events to happen at the same time? Einstein puts it like this. He says, you have to be able to have a method by which you could test this question of whether the two events are simultaneous or not. If we do not even have the conception of how to test whether they're simultaneous, then we might be using a word that doesn't even have a scientific meaning. So he says, let's try and make sure that we could have such a robust and clear understanding of simultaneity that we could perform some type of physical experiment to see whether the two things happen at once. So what test could be given? Here's what Einstein suggests. So he says, go ahead and measure the distance between the 2 points A and B. That then forms a line segment. Every line segment has a midpoint, the point which bisects the line in half. So let's designate that midpoint here as M. Place a motionless observer here at the midpoint M. So this person observes the 2 points in space A, B from their position at the midpoint. Now, Einstein says this next. Since he's equally distant from A and B, that's why he's at the midpoint, that much is held fixed. So the interval of space between A and M is the same exact interval as from B to M. Now, suppose that this individual at the midpoint who is motionless, standing still, observes the two lightning strikes within the same field of vision. That's also stipulated. He has to be far back enough to at least see the two regions in his field of vision. If he's not far back enough, supply him with mirrors or something so that he can use those as the tools of observation. But given his midpoint position, if he has a visual perception in which both of the events happen at once, then relative to him, we can say they're simultaneous, but only if we add one further additional assumption. That further assumption is that we assume that the speed of light is always fixed and constant, so that the speed of light from A to M is the same exact speed of light from the direction B to M. Why is it key and important to make that last stipulation? Because if the speed of light was different from either of the two directions to M, then even if they arrived at the same point, we could not infer on that basis that they had departed at the same point, like if they're moving at variable speeds. But on the assumption that they do move at the same and fixed speed, then here are the reasons that we can infer they've departed at the same time, because we hold fixed the distance. A to M is equal to B to M. The velocity of the light source from A to M is the same velocity as from B to M, and they arrive at M at the same moment. So they must have departed from their respective origin points at the same time if they've traveled an equal distance at an equal velocity and arrived at a common endpoint at the same time. So we have defined simultaneity relative to the motionless observer, and the basic idea is that two events can be seen as simultaneous if relative to some observer, the light signals from the two events arrive to the person's eye at one and the same moment. But it gets much stranger than even that, because now let's consider adding a second observer to the scene, placed on this train that's moving from left to right with constant velocity v. So suppose that this observer, who's positioned in the moving train, traveling from A towards B, traverses the midpoint along their way. We'll call this midpoint, as seen from the position of the train, M prime. But it's just the same line that would go all the way down and strike through M. So it's this plane that is the midpoint in between A and B. So suppose this. Suppose our train traveler surpasses this midpoint and intersects with it at the exact split moment that the other guy standing still at M conducts his observation and sees the two things from his vantage point as simultaneous. Can we remember what would be the experience of the second observer who's in motion going towards B and away from A as they pass the midpoint? For this observer, the two events will not be simultaneous, but who can tell me, perhaps, which of the two events is going to be the first event in the order of the perception of the traveler on the train? Which one will be seen first? You say B? Yeah, type it in. It's B. Can anybody tell me why, though? Why is B our answer? Let's see. Let's see if we can get that answer clear. It's correct. B is the first event seen by the traveler who passes the midpoint with velocity v. To the other observer, they're seen simultaneously. To the second observer with motion going in the direction of B, B is seen first. But I would love it if someone could just tell me the underlying reason. What is the reason that the second observer will see B before A? Why? Let's see if you guys in the chat can tell me really quick. 1 second and see what response we might get. It's not something I think that's too hard to understand, but it might take you a moment. So go ahead, wrestle with the thought, whatever you need to do. But why is it that B is the first one that the second observer will see? They're not simultaneous to the second guy. Why not? B is first, but why? I'm not going to answer my own question, so just give me something. Relative to a state of motion, yes, Cordy, correct. But I'm asking you this more detailed question. Why specifically is B the first one that he sees? Cordy, you say, no, you've already said that. Okay, so that's a good starting point. Yes, it does have to do with his state of motion. Okay, now Sydney, you say this. There's a smaller distance between observer and B than there is between the observer and A. Yes, and Cordy, you add different state of velocity than the motionless observer. Yes, it's a different state of velocity, Cordy, but there's more detail that you can add. Specifically, with respect to the second observer, they're getting closer to B than to A. So, I mean, anything can have a different state of motion, but we're asking about the specific example here of the person who's in motion, what they're looking at. and what they're moving towards and away from. So the observer on the moving train is collapsing and closing the distance between themselves and B. So they're quickly hastening towards B and getting closer to it and farther from A. So whereas the first observer stays positioned motionless at M, the two light signals relative to them reach them at the same time because they're traveling an equal distance to meet that person. But the second observer is rushing ahead of the midpoint at the moment that the first guy does his observation. And so the two light signals have different distances to travel to reach him. B has less distance to travel to meet his eye than A because he's opened more space between himself and the midpoint ahead of A than with regard to B. And again, I'll just quote Einstein here on the same. So 1 second. Yes, so when we say that the lightning strokes A and B are simultaneous with respect to the embankment, we mean the rays of light emitted at the places A and B where the lightning occurs meet each other at the midpoint M of the length AB of the embankment. But the events A and B also correspond to positions A and B on the train. Let M prime be the midpoint of the distance AB on the traveling train. Just when the flashes of lightning occur, this point, M prime, naturally coincides with the point M. But it moves towards the right in the diagram with the velocity v of the train. If an observer sitting in position M prime in the train did not possess velocity, then he would remain permanently at M, and the light rays emitted by the flashes of lightning A and B would reach him simultaneously. But in reality, he is hastening towards the beam of light coming from B, while he is riding on ahead of the beam of light coming from A. Therefore, the observer will see the beam of light emitted from B earlier than he will see that emitted from A. Observers who take the railway train as their reference point must therefore come to the conclusion that the lightning flash B takes place earlier than A, and we thus arrive at the important result that events which are simultaneous with reference to the embankment are not simultaneous with respect to the train, and vice versa. Okay, so just to be clear, Cordy and everybody else, it has to do with the asymmetrical distances between the observer's eye and the two respective light sources. They're coming from points A and B, but since he's in a state of motion rushing towards B away from A, he's going to have the signal from B reach him faster because it's simply less distance and they both travel at the same velocity. So going the same velocity and traveling two different distances, one can't reach him at the same time as the other. And that is so puzzling and deep. When you really think about it, the implications are far-reaching. What it implies is that all the moments of space-time are equally real and that there's no linear ordering that's subjective in the time sequence. If we had a third observer going in the opposite direction of travel, towards A and away from B, they would see the opposite sequence of events. They would see A occur before B. Now, Cordy, let me see your statement here. I'm confused by the stipulation we went over previously. If this observer sees two events in same visual perception, if he's sitting in the train going toward B, how is that a fixed condition? What is your confusion, Cordy? You're confused because you don't understand how he can see the other part of space? Is that what your question is about? Like you're wondering, is he positioned in such a way that he can see the two things? Is that your issue? Let me know yes or no. How he can see A behind him? Oh yeah, no problem, Cordy. That's not an issue at all. He's got mirrors. Done. Mirrors. It's mirrors. He says that himself. Einstein says this. He says, the observer should be supplied with an arrangement which allows him to visually observe both places A and B. Two mirrors inclined at 90-degree angles could be the arrangement if he's not far away enough. So don't worry about that. It's not at all, no one should think that, okay? Because I've seen this misunderstanding before. People, I submit essay prompts on this topic, and I've seen people turn in work that says this. The guy on the train doesn't see them at the same time because he simply can't see behind him and he doesn't see what's going on back there. That's not it at all. It's nothing to do with that. So it has to do with the speed of the light signals as they're trying to reach his eye. He's not blocked from seeing them. They will reach him when the speed carries the light signal to the eye. So there's no issue with him being blocked, occluded from view, can't look behind him, none of that. Okay. So good. But now are we all clear? We're all clear, Cordy. See, that would have not been a relevant point that the train somehow obscures from view some pieces of the visual field. Otherwise, this would be like a trivial example. It's like, oh, he's wearing blinders so he can't see it. But that wouldn't have anything to do with physics. That would just be a contingent fact about his conditions of viewing. So we make sure to supply him with the means to look at them, and when the light signals arrive, he will see them. He's not blocked or prevented from that. Okay. As I was also saying in the midst of your point, if we had a third observer who is going in the opposite direction of travel towards A, away from B, if they bypass midpoint at the same time that the other two individuals are aligned with them, then they're going to see the other event happening first for the same reason in parallel, because they'll be closer to A than to B, and in that case, they see it in the opposite order. So with respect to the same two events, A and B, there's no fact about what the order they happen in. In one account, they're simultaneous. In another, it is first B and then A. And in another, it is first A and then B. So when you normally think about events in time, you think there's an objective linear time sequence. Like today, this is happening, and tomorrow, that will be happening. But tomorrow is not before today or at the same time as today. But what Einstein is showing is that any two events in space-time can be seen as simultaneous relative to the possible condition of some given observer. Like when you look out, again, take the case of looking at distant galaxies through a telescope. At the time that you look at those objects, you're seeing them as they were, I guess, in the past. But at the same time, you're not looking at a video. You're seeing live images of the thing, and that's just how long it takes the light to reach you. So in a sense, you can consider those events simultaneous to whatever it is in your local environment that you're also able to observe in the same moment. And given the possible distances that a person could be at in space and their velocity, any two events could be assigned as simultaneous relative to that possible observer. Relative to this observer that's moving in the train going from left to right, B happens in the present and A happens in the future. But to the other observer going the opposite direction, A happens in the present and B happens in the future. And neither of them has the objectively correct assessment of the order of events. So it's very deep. Now, I wanted to add to the discussion and understanding of this Einstein material by talking to you about a further couple of implications that it has that are often discussed in physics and in philosophy, and it's just pretty cool. So what I wanted to talk to you about next is the phenomenon called time dilation. Time dilation is a feature of Einstein's theory of relativity that has to do with how time passes for objects or for observers that have different states of motion or different velocities. So the best way to explain and demonstrate time dilation is through the example of the light clock. So here, look at this. Suppose that these two things are planes of mirrored glass. So they reflect light. As you guys know, when you look in a mirror, you can see your reflection because light shining off the surface of that object bounces back to your eyes and collects the image shown in the reflection. So here we have two planes of mirrored glass. Let's take a photon of light, and we're going to bounce this photon up towards the top plane. Now, because this is a reflective surface, it's going to reflect that photon back down. And since the bottom plane is also the same, it will shoot it back up. So now what we will see is this bouncing photon that's simply going up and down in between the two surfaces of the light clock. And now, because it's doing this at a constant rate, because the speed of light is fixed, we will use this as a time measurement device. So let's just suppose, for the sake of illustration, that each complete cycle touching the top and then the bottom is like a 1 second interval of time on your clock. 1, 2, 3. And it just keeps doing this perpetually. So now we've made it a light clock, which can be used to record units of time in seconds per each cycle that completes. Now, let's say this. We're going to have another light clock, two of them. This one is above. Okay. And this one's below. And now let's place an observer here who can observe both. Now, let's say that the two light clocks are in perfect synchronicity. So they're in sync. They're moving in tandem. So for every cycle of one, there's a cycle for the other, and they're perfectly synchronized. That's while they're both at rest, relative to this motionless observer. But now I want you to imagine that we change the scenario just a bit. Let's take the top light clock, and suppose that we accelerate it to the right, very, very fast, with some very extreme velocity v, perhaps close to the speed of light or something. This one remains at rest, with our motionless observer who's just hanging out with it. But the one on top, we're going to send it to the right really, really fast, super fast at, ultra fast speeds. Now, I want to ask you to imagine something in your mind if you can. It's a visual you need to try and process here. With the first light clock above, let me start that one more time. The one with the other light clock below, since it's at rest and you're resting with it if you're the observer, the angle of approach that you will see the photon take as it makes its journey from the top to the bottom plane will be a straight vertical line because it's just bouncing up and down between these two planes and it's standing still. But if you remain at rest while the top light clock starts accelerating to the right very fast, you're going to see a different angle of approach that this photon will appear to take as it's now in motion while you stay at rest. So who thinks they could guess, perhaps? What will be this different visual phenomenon that the observer will see when they try to see the top light clock, which is now moving so fast? What will be the angle of approach? Well, Angel, I like that you're already on top of it and saying horizontal line, but not quite horizontal, because horizontal would mean that it never touches the top or bottom at all. And it still is a light clock. It's still functioning as a light clock, but you're on the right lines. Never mind the pun. You're on the right idea because it's going to no longer be a vertical. It won't be completely horizontal because in that case, it would never tap the top or bottom. So can we try another alternative to horizontal line? It's close. What do you think will be the perceived angle of approach of the photon going up and down between the two surfaces? Okay, Kylie, you say zigzag. That's good. I would have put it with the more formal diagonal, yeah? It's a diagonal. It's going to look as though it takes an angled approach. So why is that? Because it's being accelerated so fast that the eye, which is tracking the bouncing photon, will see it in that path of motion as though it's moving diagonally, okay? So like this would be the phenomenon. While this one continues to bounce vertically, this one going so fast is going to seem as though it's doing this. And the faster that it's going, the more stretched out and gradual the angle of approach of the diagonal will appear to be. This is not unlike a phenomenon that maybe you are familiar with. I mean, I actually know you're familiar with it, even if you haven't heard it defined before, the Doppler effect. So that has to do with the transmission of sound waves to the ear. Light, according to physics, has both particle and wave-like properties. So the wave-like properties of light are the reason that this phenomenon has some similarities to the Doppler effect. So let's talk about sound waves. When you're in a car and you're driving around, say you honk the horn. If you're in the car and you're moving with the car, when you honk the horn, you just hear that solid monotone beat. Me, me. But if you're not in the car, say you're a pedestrian, and a car rushes past you going fast, and the car's honking the whole time as it goes past, there's a modulation in the pitch of the horn as it makes its approach to you, the stationary observer, and as it departs away from you and drives off. The modulation of the pitch, what do you think, according to your memory, it is? As the car approaches you with the horn being honked, is it getting higher in pitch or lower? And as it drives off, again, is the pitch getting higher or lower as it drives off? That's my question. What is the auditory phenomenon experienced by a stationary observer as a honking horn car drives past them on the approach and on the departure? So does the pitch get higher or lower on the approach? Let's ask that. It does get higher. It gets higher. I'm not talking about volume, guys. It's not just like, oh, it gets louder. We're talking about in terms of versus it's higher. It's a higher pitch. And the reason for that is because your ear that hears the sound wave is capturing these auditory sound waves that are collected by your ear from the object that emits them. But as the distance between the fast-moving object and your ear compresses, gets smaller, that causes the amplitude of the sound waves to be more spiky, and that produces a higher pitched tone. Now, as the same fast-moving car is driving off away with some velocity, it's causing the distance between yourself and the thing emitting the sound to be longer, which causes the sound wave to be more gradual and elongated, producing a lower tone. So that's why, whether it's music being played, an ambulance siren that you are hearing, or simply a person honking a horn, On its approach, the pitch appears higher, and on its departure, the pitch starts to sound lower. So like a car zooming past you, you might hear, that's higher as it gets close, lower as it goes farther away. But if you're in the car, you're not driving around hearing, you're just hearing the same sound because you share its state of motion in that case. In the same way, if you were the observer here and you were positioned on the moving light clock, you would not see it moving as though diagonal because you share its state of motion. So with it, you're going to see it going straight up and down. Like if you flipped a coin while you're driving a car, you, the driver in the car, is just going to see it go straight up and down. But to an observer outside, if they were able to visually track it, it would look as though it's taking an angled approach because it's moving. So then, we continue the example. Given the fact that the top light clock has this more gradual angle of approach, question, suppose that we allow this top light clock to continue being accelerated very fast while the other one stays still. And I don't know, it orbits the Earth several times going super, super fast. Finally, we allow it to come back and to reunite with its twin, the other light clock. And now, what they've been reunited, they're both motionless again. Question. Since they had different states of motion, the top light clock moving so fast, changing therefore with respect to the observer, the appearance of the angle of its approach, which of the two light clocks will have recorded more seconds elapsed? The one that's motionless, going straight vertical, or the one that's in motion, taking this longer approach? Therefore, the one that is in a state of rest is going to show more seconds recorded once they've been reunited together.
Well, it's not in rest.
Well, it's in rest relative to the other one that's moving fast. What's your question?
When I think in rest, I think like it's just sitting there, like not moving.
Oh, like not working at all?
Yeah.
No, we're talking about like running versus sitting still.
Oh, okay.
That's all. Okay, so like this one doesn't have motion.
Mm.
When I say that, though, I always have to say it relatively because, you know, there could be another object in space, looks at the planet Earth, sees it sitting there, and it's like, but the whole planet's moving. So anyway, relative to the other light clock, it's at a state of rest. Now, you've heard the commentary from our student in class, everybody, right? The question was this. Of the two light clocks, which one will have elapsed more seconds when they're reunited? The one that was standing still the whole time, or the one that has been moving very fast? The one that is standing still will have recorded more seconds, and there's a simple physical reason for that. Because for it to complete one cycle, touching the top and the bottom, it only has to travel this vertical line distance. But the other one that's been accelerated very fast, depending on how fast the acceleration is, it's going to cause this angled approach to be more gradual. So that simply is a longer arc for it to travel, to traverse one complete cycle. So while this one's bouncing up and down, like that, the other one is appearing to go at a slower rate because of the additional length of each cycle. So this is so strange because imagine that these two clocks were produced at the same time and they came off the assembly line of the factory at the exact same moment. That means that they started their existence at the same time, but now they're not the same age. Now one of them is older than the other. Which one is older? The one that has recorded more seconds passing is older than the other one that's in a state of motion. And you may think that's an illusion. They can't be different ages, but they are. And that's simply the result of one thing moving faster than another thing which remains at rest. And it keeps getting weirder. Suppose that we have two observers. This one stays at rest with this light clock. Let's say that the other observer moves with the other light clock and travels with it. If these two observers were twins that started off being the same age, then when the one that's been moving fast is reunited with his twin, he's going to be surprised to see that that twin is now older than him, even though they were born at the same time. Because he's aging at a different rate, because clocks are moving at different speeds relative to the other observer who stays at rest. This gives rise to a very famous kind of puzzling implication of all of this, which is the twins paradox. Okay, so I'll next explain the twins paradox. We had to use the light clock first to get you there. Now, that opens up discussion of the twins paradox. Okay, so take the case of identical twins, yeah? Identical twins are the same age, as you guys would know. People, I mean, basically, a couple hours, minutes, whatever difference, but for the most part, same age. Going through life at the same age, but your sibling. I have triplets that are my siblings, so I mean, I'm all very familiar with this. But anyway, two twins that are born, take away, they're same age. So let's take this case. Place one of the two twins in a rocket ship that's going to accelerate away from the planet Earth very, very fast, maybe even approaching the speed of light. Now, their other twin remains on the planet Earth at a relative state of rest compared to their interstellar traveler twin. Now, after the twin that's been moving fast through space in the rocket ship comes back to planet Earth on the return, they're going to see something that's very shocking in a way. Well, maybe they wouldn't be shocked because if they're, a physicist or an astronaut, they would know these things. But they will come back and they will see that their identical twin is now what? Older or younger than them. So the one that stayed on Earth is older or younger after the reunion of the one that came back from space. Tell me the status of the one that's back on Earth. Older than or younger than the other twin? Older than, correct, Kylie, for the same reason given here. Now the motionless or the terrestrial Earth-bound twin is kind of like the motionless light clock. And the twin that's moving fast through space close to the speed of light on a rocket is like the accelerated light clock that's going very quickly. And so, how weird is that? You would have thought that when two people are born as twins, they will never be different ages. But definitely that would happen in case we had the means by which to accelerate people at such great speeds faster than others that remain at rest. So time is relative, guys. It's not absolute. This completely rejects ideas that Newton had, that nothing you do in space can possibly change the rate of passage of time. Newton thought that time is absolute. It moves at a fixed and constant steady rate. And no matter if you're going fast, slow, or not moving at all, the passage of time would never be affected by that. What Einstein's showing us here is that that's not true, that depending on your state of motion relative to other observers in space and time, time will pass at a different rate for you as opposed to those others. Now, this isn't just philosophy, this is science. This has been empirically proven. So if you're sitting there wondering, how is this weird stuff true? It is, it's been proven. I mean, at least if you believe that science can have such a thing as proof. For example, one method of proof was in the middle 20th century. We had two atomic clocks, and they were perfectly timed, and they're so precise that they record time down to 1,000 decimal points, like tiny nanoseconds, right? So they're in complete synchronicity, these two light clocks. Place one of them on a jet that could travel at high rate of speed, I mean, nowhere near the speed of light, but maybe several times the speed of sound, like a Mach jet, and keep another one on the surface of the Earth, motionless compared to its one in the jet. The mathematical prediction of the time dilation that will be recorded between the two, the variance in elapsed time, is exactly in conformity with what physical experiments showed. And that's just one case. Another way of proving it is with particle accelerators. So it's not possible really to accelerate macroscopic objects at the kind of velocities that we're talking about. For a human body, for example, putting you anywhere close to the speed of light, the forces would just rip you to pieces. But what we can do is accelerate tiny little physical elementary particles in these particle accelerators, like very close to the speed of light, even above 90% of the speed of light. And take, for example, the particle called a muon. When we put these inside of particle accelerators, we notice that their half-life extends, and therefore they basically are living longer than other particles that are not excited with that same state of velocity. And this is all proof of the theoretical results of Einstein's work. So, at least in this one case, I kind of feel like it's not really debatable. I mean, this stuff has sort of been proven in physical experiments, so it's very hard to challenge. But it has such wild results, So with the twins paradox and time dilation, we can see that there are these far-reaching and bizarre implications for our own understanding of ourselves and the universe, according to space-time theory. One more question before I start speaking about Ted Sider a little bit, the next author. If this concept of time dilation is real, as it at least scientifically appears to be, let me ask you this question and ponder this if you can. Why then don't we notice it happening in our lives? So if it's really true that time dilation exists, then how come people, for example, who take a lot of flights and jet setting around don't age slower than people who stay on their couch and don't do that? Or how come we don't have to keep on resynchronizing our watches because some of us are driving around the freeway and running while other people are standing still, so time is passing so much slower for us than them that our watches get out of sync? How come those things are not observed if time dilation is real? What do you guys think is the answer? I'm saying time dilation is a real phenomenon, meaning that basically here's the takeaway rule. Things that are moving faster through space are moving slower through time relative to other objects that don't have that velocity. So if this is true, then how come we don't see it or notice it in our everyday lives? How come when I get off a flight I don't have to check to make sure that my watch is out of sync with everyone else's. I'm not talking about time zones, guys. Please don't think that's what I'm talking about. But, the rate of the watch moving in terms of its clock hands. Simply stated, once again, give me an answer. If time dilation is real, how come we don't notice it when we achieve different speeds in our everyday lives on this planet? Why don't we notice it? There's an answer that's pretty easy to give if you just think about it. So think, why do you think that we don't notice the phenomenon of time dilation in life, in everyday life? Okay, Brandon. There you go, very good. And same to you, Cordy. You guys have got it. So I knew you understood it. It's because, correct, we cannot achieve such variable speeds to make the phenomenon anything more than infinitesimal and undetectable. So for these time dilation phenomena to be noticeable, we would have to be going really, really, really fast compared to other people. But the variable speeds that we actually can achieve within the constraints imposed on us as beings on the surface of the Earth, they're not that great. Even with modern technology, I mean, how much faster than you could I possibly go? Maybe 600 miles per hour or something if I'm in a jumbo jet, or if I actually fly in a space shuttle, maybe I could go a couple thousands of miles per hour or in a fighter jet, but I cannot go anywhere close to the speed of light. The speed of light, for those that don't know, is 186,000 miles per second, or 300,000 kilometers per second. So not per hour, per 1 second, 186,000 miles. So we can't build anything that can travel that fast. We can't necessarily withstand forces that could go that fast. But look, if we could, if we were beings that were capable of going like close to the speed of light while other people stayed at rest, then everything would be all messed up with our clocks. We could never keep them in sync. Some people would be aging way slower than others. You have kids, then your kids would be older than you if you started moving really fast and you left them behind staying slow. This reminds me of some scenes from the film Interstellar. Yeah, so some of you guys might have seen Interstellar. I know it's a bit of a modern classic. I really liked it, and it was with Matthew McConaughey and stuff. There are some scenes in the movie that might seem confusing to people that are not versed in a little bit of the space-time theory and these physical results. But they're not just like crazy science fiction stuff. I mean, it is crazy science fiction stuff, but it's drawn from actual science. So here, for example, one element of the movie. I hope I'm not spoiling it too much for anybody if you haven't seen it, but anyway. Matthew McConaughey is this like astronaut, interstellar space traveler. And he goes on these missions, I guess, for the U.S. government or something. I can't remember exactly all the points of the plot. But anyway, he's traveling in these vessels that are taking him close to the speed of light as he does his stuff. Now, he comes back to the planet Earth after this like long mission. And when he comes back, one of the last scenes in the movie is he's giving aid and comfort to his daughter who's on her deathbed. But the thing is, his daughter is older than him in age now because of the fact that she stayed on the Earth while he was out there traveling so fast. And that meant that his passage of time was slower relative to her. So he comes back and, his own daughter is older than him. She's leapfrogged him in age because of this phenomenon. And you look at that and you think, man, isn't it impossible to have a kid and then the kid ends up being like senior to me in terms of age? And even though we're not going to see this because, for all practical purposes, I don't think we're going to achieve such technologies to accelerate us at those rates. But it really would happen if it actually was possible to go that fast and not, die in the process. If you could, for example, enter a centrifuge that could spin you close to the speed of light for some interval of time, then depending on how fast it was spinning you and how long you were in it, you would emerge from the machine, and that would be like time travel to the future right there. So anyway, interesting and kind of trippy possibilities to consider once you understand some of the basics of these theories of Einstein. Now, I wanted to spend time at the beginning here, or really for the majority of the meeting, kind of expanding on the lessons of Einstein. That's why originally I had set two meetings for it. But I also gave 2 meetings for the next author, Ted Sider. So we're really not going to fall behind at all. And we'll start talking about that next guy now and continue with him on Monday after the week. So the next author on this topic of time is the American philosopher Ted Sider. He goes by Ted Sider to people that actually know him. I know some people that are friends with him and stuff, but academically, he goes by Theodore Sider. Okay, he's born in 1967, and he's still alive. He does a lot of work in metaphysics, and he wrote a book in 2005 that is contained, one section of it in our anthology, in our textbook. So from 2005, and it's just called Time. So Ted Sider, Time, from 2005. So I'm just going to try and set up the initial ideas of his paper, and there's much to fill in on Monday after the weekend. So to begin, he says this: I really kind of want to explore the puzzles and paradoxes that happen when you start to think about time in depth, when you go beneath just the surface depth. Oh, what time is it? How much time is there before I have to go to work? When you start thinking about it in a theoretical and a more deep scientific sense, it's really trippy and bizarre. And he says, I want to try and explore philosophically the weird aspects of time and try and, wrestle with those. He says, one of the strange things about time is the way that we say it moves. Now, we just take time for granted. It's hard to question its nature. It's kind of like the air that we breathe. When you're breathing, you don't just sometimes take a step back and be like, but how does breathing work? What is inhalation and exhalation? You just do it, right? Once you start thinking about it, it almost starts to seem like a labored effort. Like, man, I'm doing this all the time without even thinking. Time is sort of like that too. We live with time. It's a fundamental aspect of our daily lives. But most of us will never, unless we take a philosophy or a science type class, step back and ask those deeper questions. What is time? How does it work? What is the best theoretical current understanding of it? But Ted Sider says we should question it because once we investigate it beneath surface level of depth, our ordinary ideas of it, our common sense ideas of it start to break down and make no sense. And one of those weird things about it that he says we have to try and understand is, what does it mean to say that time moves? Okay, so here's his first big claim. Time is puzzling because people say that time moves. Sorry, this pen's not exactly the best of my pens. Say that time moves. But follows that by a question. But what does it mean to say that time moves? What does it mean to say that time moves? Okay. Now, let me ask you guys for some quick input. There's a lot of kind of common expressions, popular sayings, that have the message behind them that time moves in a certain way. Can anybody think of like a common phrase or little one-liner that expresses the idea of time moving?
Time flies.
Okay, good. So I want to put that in the chat. Some say time flies. Yes. What is to fly? To fly is a state of motion. So time flies when you're having fun. Correct, Cordy? Correct, Angel? What else? People say time marches on, like as though it's moving in a marching state. Sometimes people say time is running too fast. Running, again, is a state of motion. Sometimes when things are boring, you say, oh man, this is like the worst, most boring thing. Time is moving so slow. It's just really moving so slow. Moving slowly is a state of motion. People say time passes, like it's passing. Passing something physically would be to move past it. Time marches on. Sometimes people say it flows, as though flowing in a river, like a state of motion. Well, anyway, all these different cliche or common phrases show that when we think of time, if we think of it at all, we think of it as something that is moving, and we are somehow caught up in its flow, the flow of time. Like as if it was a river that's moving, and we're just sort of on that river being guided along and taken by its current. But the author says, not so fast. Let's ask a deeper question. What does that mean, though, to say time moves? And this is actually not so easy to explain. The reason is because there's a paradox here. To even give a definition of the concept of movement at all, time has to be referred to. So next point, I'll put it here. What does it mean to say that time moves? Just to give me a little extra room, put it over on this point of the board. What does it mean to say that time moves? This is puzzling because time is needed to even define motion. Okay, so okay, so what it says here is that this question and answering it is hard, it's confusing, it's puzzling. Why? Well, it is because to even explain what motion is, you need to make reference to time. So Follow me here. I'm going to show you something moving. And it'll be an easy example. So see this, I guess, marker that's in my hand here? So let me see what I can do to kind of make this visually clear. This is my wallet right here, okay? And then this is a marker. So this is a pen. The pen right now is positioned on this wallet. And what's going to happen is it's going to move from the wallet over to the marker. Ready for this? Wow, it happened. We did this. So the marker moves. Question though. Thought I could balance it. But anyway. Question. For that to happen, for it to move from point A here to point B there, it had to be in different places at different what? For anything to move. The definition of motion is to be in different places at different what? Times, exactly. Motion means you go from point A to B over time. So for something to move through space, for motion to occur, time has to be referred to in the analysis of motion. If something stays in the same place at all times, it's not moving. So if I stay in this chair that I'm in right here for the rest of all time, I will never move again. So moving means I have to be in different places at different times. Like this morning I was in Long Beach at like 8 a.m. Now I'm in Chapman and it's whatever, 10:45 a.m. So I've moved from point A to B. Motion requires reference to time. Without the notion of time, there's no way to explain motion. For a thing to move, it has to be in different places at different times. So now, if people say that time moves, plug it into the definition of motion and you're going to get a weird, confusing, infinite regress. Saying time moves is like saying that time is in different places at different what? Times. But now we're using time to define the motion of time itself, which is like using the concept to be explained in its own definition. So if we say time moves by being in different places at different times, then what is the second order time that time is moving with respect to? I mean, objects move in space with respect to time. But if time moves with respect to time itself, then it looks like we have no answer, because then we could ask, well, what is the second sort of time that first order time is moving with respect to? And then we would have to place that in a third order time sequence. And it would continue on as an infinite regress, so we would never be able to explain the concept. Therefore, he says, we're really tied up in knots trying to even explain what it means for time to move. Now, there's more to say about this. I can't really rush through all of it in the last few minutes of class time. But we'll finish on Monday. And what he's going to basically say next is that, after giving a couple more examples, he's going to say, all right, well, this is a hopeless paradox. There's no way to explain the motion of time because it involves these kind of circularities and loops. Therefore, we have to just give up on saying that time moves and instead just embrace the Einstein theory of space-time. Because one of the features of Einstein's theory is that, according to it, time does not move. It's just sitting there with all the events in space, and all of them are equally real, and they're all co-located in the one big space-time framework of the universe. So according to Einstein's view, the movement of time is an illusion. All the events are already set out there, and that helps to get away from the puzzling paradox of explaining how it moves. If it doesn't move, then there's nothing to explain. But of course, it's a fundamental revision to our common sense thinking about the reality we are in to think that time doesn't move. Because I know that you sitting here believe that what's going to happen later today has no definite nature because it's not a fact yet. But according to Einstein, the future and the past are just as much factually real and concrete and objective as the present moment is. So all those pictures of you back as a little kid and stuff, that point in space-time where you're a child still exists, just as much as this present moment where you're a young adult. And the later stages of your life, when you're like a full-grown adult or an elderly person, those also currently exist. So on the space-time view, nothing comes into being, nothing passes out of being. It's all just there at all times. And that's a very weird and trippy idea because it starts to undermine even fundamental assumptions about human free will. You think that you have the free will right now to do certain things and not others. But if the space-time theory is correct, then every event that you'll ever experience is fully set forth, and therefore you can't do otherwise, even though you have an illusion of freedom, which makes it seem as though you can make anything happen. I always find it puzzling and interesting to teach this kind of material, because you start off with students in philosophy and you tell them about counterfactuals, and they're like, come on, there's no such thing as counterfactuals, there's just the real world. But then you tell them that the real world's the only thing that exists and there's no such thing as possibility, and people are like, wait, no, I'm free. So it's like, which one do you want? People are all kind of tied up on these things. It's funny. They touch on that in the movie The Arrival, that time is not linear. yeah, there's a lot of really good and high quality science fiction film that deals with these heady concepts. And these are concepts that can only be thought of by people after Einstein and people after the 20th century. So unlike some of the topics in our philosophy class that we've studied, which were thought about by ancient Greeks thousands of years ago, for better or worse, here's something that it's a special treat for us because we don't have ancestors that were sitting around thinking about the theory of relativity or about the nonlinear conception of time. This is truly modern. And that's one thing that I think is kind of fun about it. It's also, relatively recent philosophy writing, 2005, instead of like 1500, 1600, whatever. Okay, guys, so there's more to say, but for now, we're running out of time. Haha. So I'll see you guys back on Monday. I'll see you back on Monday. If you're back on Monday, then it's something that's already predestined. So nothing you can do about it. I'll see you then on Monday, guys. Are we all good? Let me know in the chat, and then I'll close this out. Or if you're not going to be there on Monday, then I guess there's nothing I can do about that. Okay, thank you, Sebastian, and everyone else. Just making sure that we're all together before I close the stream. Are you all good? Just taking a few moments. Okay, perfect. So thanks again. And if you need anything over the weekend or any other time, please message me and I'll be getting back to you. I have office hours every Friday from 11:30 to 12:30, so I'm going to try to get back home quickly enough to start them on time. If I don't, then it won't be much later than 11:30. Okay, have a great one, and I'll see you back next time. Take care.